Good day to everyone. This is Rico de la Peña, and today we will be just discussing or just reviewing univariate statistics. And obviously, this presentation is not from me. This is based from Ricardo Olea of the USGS. Right, and these are the topics that we will be discussing. Basically, just univariate statistics from slide 35 to around 77. All right, now let's first define some jargon in statistics. Population basically is everything. Okay? Basically, it's the collection of everything possible, all possible outcomes of a given system or a given group. For example, population of the Philippines, population of Mapua students, population of professors. And next in the hierarchy is the what we call the sample, right? And this is quite confusing, especially for geologists, because for a geologist, a sample usually pertains to a piece of rock or a piece of sediment, or a scoop of sediment, or yeah, basically piece of rock, or it's a tub of sediment, or so on. But in statistics, sample is still a collection, but just a limited collection. So a sample in statistics is just a part of everything, or a portion of everything. And further down the hierarchy, so you have population, and sample is just a subset of the population. We finally have what we call observation or measurement, but more generally we call it observation. Okay, so observation is basically your data point. Okay, so the hierarchy is as follows. So you have your population, which is everything, and then you have your sample, which is just a portion of your population, and then further down you have observation, which is just one data point. Okay? So a sample will consist of multiple data points, right? And my analogy here is basically let's use the upcoming elections as your example. So the population here, for the purposes of talking about the upcoming presidential elections in 2022 May, the population is all the Filipinos that are eligible to vote. Okay, so that's your population. And then your sample. So let's say Pulse Asia, the statistical and surveying company, decided to have a survey. Okay, so they can only take so much. They can only have so much correspondence. They can't. They're not capable of asking or talking to all the eligible voters, so they just take a small subset of all the eligible voters, and that would be your sample. Let's say, for example, 2,000 correspondents. So that would be the sample, the 2,000 correspondents, and one correspondent will be one observation. All right. All right. Now the next concept is what we call a random variable. Basically, it's a variate or variable that can have a value or quantity that can vary. Okay, it can change, and its value is just within a given range. Okay, and a good example of a random variable is a dice roll. Okay, so a dice roll. Okay, so just throw a dice, and its value can be anywhere between 1 to 6. Okay, Now we have, for statistics, we have this what we call a descriptive analysis. It's a procedure of doing statistical analysis. Uh, the point of doing descriptive analysis is to systematically and objectively answer a question or probably a hypothesis using statistics. And it has like 6 steps. First is you determine your objectives. Okay, so of course you have to know what question are you trying to answer. And in order to answer that question, you have to break it down into several objectives. Okay. Second step, of course, you collect your data. You can do this by using questionnaires, measurements, data mining if you're sophisticated. Next is you clean your data. So you look for outliers, errors. Okay. And in here, the use of summary statistics is very useful, and you will see later on. Next step is data analysis. Basically, we summarize our data. And then further on, we interpret the results in relation to our question. Okay, so have we answered? Were we able to answer our question? Is it a yes or a no? Okay. And finally, we have to communicate the results. And that with that, we have to do some data visualization. We have to use the appropriate or aesthetically suitable plots or graphs or figures. All right. All right. There are many ways to visualize your samples. One of which is your frequency table. Okay. Basically, we just have to. This frequency table is used for just one variable. So just one variable and multiple measurement with multiple observations. And what we do here is we just cluster together the your collection or your sample into bins. Okay. So we try to group. You will try to like divide the data into bins that are more or less equally spaced apart. And then for every value is that goes inside the bin, we just count. We just take a count. Okay, like in the example here, this is an example from an oil company, and they have a data on the depth to a geologic unconformity. Okay, and you can see here different. You can see here different values of depths to an unconformity, and it's expressed in feet. Okay, and what we have here is a frequency table. Okay, and what they did here is they divided and yeah, the range of values here starts from 7,680 to 8,070 feet. And what they did here basically is we just divided the data into equally spaced bins. Okay, so these are the classes or the bins. So these are also called the bins. And then we just counted how many data, or sorry, how many observations actually go inside these bins. So for example, for the first class, we just have one count. And then in this class 7, we have like 10 counts. And then for class 9, we have like 13 counts. Okay, and then the next step is to take their percentage. Okay, so that would be the frequency. So all you have to do is just take the sum of all your observations, and then take the count, divide it by the total number of observations, and express it as a percentage, and that would be the frequency. All right. All right. Now next, another way to express or to visualize data, specifically univariate or single variable data, as your histogram, which is basically just a frequency table that is visualized as a chart. Okay, and you can see here the x-axis is your bins, and then the y-axis contains your frequency, okay, your percent frequency. And this is nice because we can quickly see visually which bins or which classes are the most frequently occurring. So you can see here the class that is centered at the value of 7,935 feet is the most frequent value, while the least frequent values are these classes. Okay. Another way to visualize data is by using your what we call the cumulative frequency. Sorry. So this is basically like just like the histogram, but instead of just plotting the frequencies, we actually uh, add the frequencies together. Okay, starting from the lowest value class, starting from the bin with the lowest value. So as we go to the next bin, we add their frequencies, and so on and so forth until we reach the last bin. So it should be around 100%. Okay, as we approach the last bin. Okay, and customarily, sometimes we plot this chart. Okay, we scale it so that the line would actually look straight. Okay, so sometimes we have to play with the y-axis with the scaling so that this cumulative frequency plot would actually plot as a straight line. Okay, sometimes typically we use some logarithmic scaling. All right, now let's talk about summary statistics. And basically, these are values which represent which summarize your data, your sample. So basically, the use of summary statistics is a data, instead of presenting a buttload, a table containing buttloads of data. Let's say, for example, a sample that contains like 1,000 observations. So instead of presenting that buttload of data, you can just summarize their parameters. Like you can basically use summary statistics to show what is their central value, how much is the data scattered, how big is the scatter of the data. Okay, are they like tightly clustered on one value, or are they dispersed on a huge range of values? And what is the shape of your this data distribution? Okay, and yeah, our first let's first discuss the measures of location or the measures of the data centrality or the central tendency of the data. And we have here the mean, the median, and the mode. Mean is basically the average, so just sum up all the values and then divide them by the number of observations. The median is basically the midpoint. So you list down the data and then you look for the midpoint data. And then the mode is the most frequently occurring value. All right. Now, for the mean, uh, strictly speaking, there are three types of means. And for statistics, we usually just use the arithmetic mean. And this is actually useful for values that are linearly increasing. Basically, for most cases, it is actually useful. But once we start dealing with data that wherein the values are exponentially increasing or stepping exponentially, like earthquake energy data, okay. So as you may know, the Richter scale or the scale for the earthquake magnitude is it goes from like 5 magnitude 5, 6, 7, 8, 9, 10, and each step is actually exponential. Okay, so each number in the scale is one step in the scale corresponds to exponential increase in energy. So basically, that's how earthquakes generally behave. Okay, they tend to be distributed. Their energies typically increase in an exponential manner, and for their geometric mean might probably useful. Okay, and we have another type of mean here that we call harmonic mean. Harmonic mean is useful when you're dealing with velocities. Okay, example seismic velocity and Darcy velocity. Okay. In harmonic mean, we actually take into the account the amount of distance traveled, the proportions of distance traveled by your wave or your groundwater. Okay, so when you're dealing with velocity, you cannot just simply average the values, okay, because you have to take into account the distance traveled, okay, through the different layers. Okay, okay, so yeah, harmonic mean you will need this if uh, you're dealing with velocities, okay, where time is actually important. Probably discuss that later on. Median, this is good for when you're expecting extreme values in your data set. Okay? Okay, so if you're kind of anticipating that your data will have like really extreme values, median is good for sort of mellowing down the effect of extreme values. And the most common example application of median is for income distributions, like for the income of the poor and the rich. I mean, when you're talking about income of people, I mean, you can have like really extreme values with the extremely poor and the extremely rich people. Okay, so they tend to be outliers, and in here, median would be really useful because you're basically just looking at the midpoint still. I mean, you're just arranging the value by rank or by order, and then you're just trying to look at the midpoint. Extreme values can do little to mess up your median values. Okay. Mode, this is your most frequent value. Okay, and this is useful when you're dealing with classes or basically when you're dealing with multiple variables or multiple classes. For example, you're doing a point counting of different minerals in a rock sample in a petrographic microscope. So you cannot just average together the number of counts of quartz and plagioclase. So you have to count them individually. Okay? And you can basically just uh, put them in a plot. You have different classes here like quartz, plagioclase, biotite, magnetite, whatever minerals you have. And from there, you can easily see which minerals is the most dominant. Okay, okay, so that's the advantage of mode. It's really useful when you have different classes. Okay, and you want to see which class is like the most dominant. Now, robustness is not necessarily a statistical summary, but it's just a description of how solid or how reliable your statistical summary is. For example, when you're dealing with data with a lot of outliers, median may not be as robust as sorry, mean will not be as robust as median. Okay, because when you're for example, you have a data with extreme values, the tendency with the mean is that the extreme values can disproportionately influence the mean. It can like shift the mean towards the extreme value, as opposed to like your median, where in the median you only care about the order of your data. Okay, so the median is not really as much as that influenced by extreme values. Okay? So in that sense, median is more robust than the mean when you're dealing with its extreme values. Now, let's talk about the measures of spread. You have your variance, standard deviation, extreme values, quantiles, and IQR. Right, variance is basically what we do here is we just take the mean of your sample and then you subtract the mean from all of the observations and then square each for each difference you just square them and then you take the summation of all those squares and then divide it by n minus 1. Okay, variance is a good measure to show how it's really good if you really want to spot presence of outliers in your data. Okay, because you're basically squaring the distance of your data from the mean. Okay, so you can quickly spot here, or variance tends to exaggerate the scatter of your data. So you can quickly spot outliers or extreme values in your data set. Now, standard deviation is basically just a square root of your variance. And the advantage of variance or the standard deviation is that the unit of value, the unit of measurement in standard dev is the same as the unit of your observations. Okay. And this one is actually, we will probably, you can see the use of standard dev later on in the Monte Carlo simulation exercise. All right, and then extreme values, basically these are your minimum and your maximum. Quantiles, this is basically quantiles is basically centered on the median. All right. So again, median. What we do in the medians, we just arrange the data in order or by rank, and then look at the midpoint. That's the median. All right. Now, for quartiles, we basically just look for the median. For example, this one, look for the median, and then for the two halves of that are split by the median, we look for their median. Okay. So median within the median, you can basically split the data into four partitions. Okay. So that's your quartiles. For deciles, we basically partition the data into 10 partitions. And then percentiles, we partition the data into 100 partitions. Okay. And I think I would like to point out some disclaimer here when you're dealing with percentiles. If you're dealing with let's say for example, you start working with the oil and gas industry or the petroleum industry, they're quite weird because my mouse. In the oil and gas industry, they have a reverse scale for percentiles. Um, Normally, if you're doing statistics in any other industry, okay, so this is your normal. This is your normie statistics. The P10 would normally be the lowest value. P50 is basically your median, and then P90 is the upper end of your values. In the oil and gas industry, it's the opposite. Okay, so their P90 is their lowest value, P50 is the median, and then P10 is basically the uh, P10 would be the larger uh, percentile value. Okay, all right. So yeah, basically in oil and gas, they just reverse the scales in their percentiles. Okay, so that can cause some confusion when you're like reading papers on oil and gas or working with oil and gas data. All right, so we just applied the quartiles on our UNCF data or the unconformities data. And you can see here, Q1 is basically just the median. And then from here, from the lower half of the median, we just again count until we reach the midpoint. And Q1 is the median of the lower half. And then Q3 is just the median of the upper half. All right, interquartile range, you can take this by basically subtracting Q3 value by the Q1 value. And it's a good summary to measure the spread of your data. And generally, it's considered more robust than variance because again, variance relies on mean. Variance is basically based on the mean, while IQR is based on your median. So when you have extreme values, IQR is more or less a more robust or a more reliable measure of your scatter of data. All right, outliers. Basically, these are your values that are either so big or so small. And the way to spot, okay, and these could be probably errors in your data, or they could be actual or legit values, but they're just really, really high because of some some unaccounted or unexplained phenomenon. Okay, so we don't always reject outliers. Okay, we have to explore if the outlier is an error or just a really weird value that probably has a scientific explanation. Now, the rule of thumb to spot an outlier is to multiply the IQR by 1.5, okay, and then plot it from the median. So, sorry, yeah. So like if so yeah. So let's say this is your median. If your median is here, you can just plot the 1.5 IQR here, 1.5 IQR here, and basically all the values in here are your outliers. Okay, your mild outliers. Now, if the data is like 3 IQR away from the median, we call it extreme outlier. Okay? All right, another a box and whisker plot is a nice way to visualize the minimum, maximum, mean, and the quartiles of your data. Okay, so basically in a box plot, you have your mean here. Your mean is like, sorry, you can see here the mean is the plus sign. The median is this heavy black line. The Q3 is this box. Q1 is this box. And then this is your maximum, this max and minimum. And you can also like plot another line, or the 1.5x of your IQR, 1.5x of the RQR to just to spot the outliers of your data. Okay. All right, measures of shape. You have your skewness and your quartile skew coefficient and the coefficient of your kurtosis. All right, skewness. Basically, what we do here is we just apply this equation here, okay? And this is based on, okay? So basically, to take the to get the coefficient of skewness, what we do here is we just uh, take an observation value, and then from there subtract the mean. Okay, observation value, subtract the mean, and then raise it to 3. Okay, and take its summation, and then divide it by n. I think this should be n minus 1, and then that value will be divided by the cube of your standard. I think this is standard deviation. Okay, and the values, you can interpret the values depend. So your coefficient of skewness. Okay, so if the skewness is less than 1 or greater than positive 1, in short, if it's like negative 1.1, negative 2, or if it's like positive 1.1, positive 2, it means that the distribution is highly skewed. Okay. Now, if the value is between negative 1 and negative 1 half, or between positive 1 half and positive 1, so let's say, for example, negative 0.6 or positive 0.6, then the distribution is moderately skewed. And then if the skewness is between negative 1 half and 0, or between 0 and positive 1/2, let's say for example negative 0.4 or positive 0.4, then the distribution is approximately symmetric. Okay. All right, so you have here in this UNCF example, you have a coefficient of skewness of negative 0.38. So more or less, this is approximately still symmetric. Okay. Okay, so yeah. And then quartile skew coefficient, I'll just skip this one. Kurtosis, this is a statistic that is used to measure the concentration of values around the mean. All right, so you're just trying to compare the distribution relative to a Gaussian or a bell curve distribution. So Gaussian distribution is also called a bell curve distribution. It is also called a normal distribution. So if the coefficient of kurtosis is less than 3, okay, it means that your data has a sharper peak than a Gaussian. So if this is your data and you have like a Gaussian, it will look like this. Okay, so this is your Gaussian, your red, and your data will be much sharper. And then if your B2 is equal to 3, it's just similarly peaked as a Gaussian. And then if your B2 is greater than 3, and it means that your data is less peaked than a Gaussian. So your data is flatter top than a Gaussian. Right, models. Let's talk about probability. Basically, it's a measure of a likelihood of an event. Okay. And then Bayes theorem. This is really a nice theorem, but unfortunately, this slide does not really give justice to the whole theorem. I'll just refer you to a separate video, okay, by a different person. Basically, Bayes theorem is really useful when you're like you have a starting probability and you want to update your belief or your knowledge of that probability with evidence. Okay? Bayes theorem is basically we're trying to measure how close we are to the truth given the evidence that we have. Okay, so I'll just have a separate video uploaded for the Bayes theorem. All right, probability functions. These are your basically your histogram. Basically, these are your functions that are used to approximate your histograms and your probability density functions or cumulative density functions and so on. And then next concept is the concept of binomial distribution. This model of distribution is useful for phenomenon or systems that we are trying to model, and that the outcome of the phenomenon or the system is you just have like pass or fail, or yeah, success or fail. Okay, so you just have two possible outcomes: success or fail, or heads or tails. And those situations are where your binomial distribution shines. All right, so let's define the important stuff here. So we have your trials, number of successes, probability of success given the number of trials. Okay, so this is an interesting model because, for example, we are trying to model the likelihood of getting a tails in a coin flip. Okay, so we know that in a coin flip, okay, we have like a probability of 0.5 of getting a tail, and similarly we get a probability of 0.5 for getting a head in one flip of a coin. Okay, so more or less you have a 50-50 chance of getting tail or a head in one flip. Okay, now if we flip the coin two times, are you gonna get a 100% probability of getting at least one tail? I think no, right? No, it's not. It doesn't happen in the real world. I mean, even so, if you flip the coin like three times, you don't get 150% probability of getting tails. Okay, it doesn't exist. So this is where the binomial distribution comes in. Okay, so it kind of models like the diminishing returns that we get with increasing number of trials. Okay, it factors in the diminishing returns of repeating the trials in increasing your chances of success. Okay, and this has a good example in petroleum exploration drilling. Probably just discuss it later on, or probably give a supplementary reading for this. All right. Normal distribution. This is also known as the Gaussian distribution. Basically, it's really the most common distribution of values. And we can basically make or simulate the distribution of a data given your some statistical parameters, particularly the mean and the standard deviation. So as long as you know the mean and the standard deviation of your data, of your sample, you can easily model the normal distribution of that data set, assuming that the data has a normal distribution shape. Okay, probability for models, skip. Expected values, basically these are the mean values, okay? Expected values are just the most likely values that you can expect. And you just, basically it's really just the mean value, okay? It's the most likely value, moment, skip. Simulation. All right, simulation, we do this when your phenomenon is really just too complex to analytically determine the probabilities of a given outcome. For example, you have a lot of inputs for, or there are a lot of predictor variables that affect the outcome, like so many inputs. For example, your soil stability analysis exercise in the Monte Carlo simulation, you have so many inputs to get the factor safety. You have your unit weight, you have your friction angle, you have recohesion, all right? And it can be complex or hard to just mathematically arrive at the probability of certain values occurring. So what we do here is we just simulate different outcomes. Okay, so you basically just do a lot of you run a lot of scenarios multiple times using randomized inputs. Okay, for example, you in the Monte Carlo exercise, I think we did like 500 or 1,000 simulations. So we ran the all the possible outcomes 500 to 1,000 times, and then from there we try to discern the pattern of the outcomes, and then from there we can derive the probabilities and the statistical summary of the outcomes. So you can get the mean factor safety, you can get the mean or the standard deviation of the factor safety, you can get the P10 of the factor safety, the P90. Okay, so you have like you can like get the P10 if you want to get the uh the the lowest estimate for the factor safety. You can get the P90 for the highest estimate of the factor safety. All right, so yeah, this is easier appreciated in the exercise, okay, or better appreciated in the exercise. Now, next concept is the concept of bootstrap. We do this when we think our data is accurate, our sample data is actually, we think the data is actually accurate, but it has a lot of gaps. Okay, so for example, you did some measurement on an outcrop and you think you did the right measurements. You think you took the representative rock samples, but due to like logistics, like it's too heavy to like collect 30 pieces of rock. So instead you collected like 5 pieces of rock, but you're quite confident that your data is more or less representative or accurate, but you just want to uh, expand or you want to get a better grasp of the true statistical parameters from your data. You want to get data. You want to take your data and get it closer to the true population mean or to population values. So you can basically expand the usefulness of your data using Bootstrap. Okay. So yeah, for example, in your example, you have like 5 rock samples. Okay, and 5 samples really is quite a small number for statistics, and you can basically increase our understanding of that data by doing Bootstrap. For example, what we will do is just put all those 5 rock samples like in a ballot box or a box that you don't where you don't see what's inside, and then what you can do is to just randomly pick one rock at a time and then record that rock, record what rock you got, then put it back again in the box and then randomly pick another rock and then just record it, then just repeat it for like 1,000 times. Okay, and from there you can more or less you can start simulating populate the true population statistical parameters of your data. Okay, so you can like get the bootstrap distribution of your mean data and so on and so forth. A more clear example is this is basically what we did in the Monte Carlo analysis exercise. So if you will remember in the Monte Carlo analysis exercise, you're only given like mean and standard deviation data for the inputs. So for example, you're only given the mean of the friction angle and the standard deviation of the friction angle. So you started with a rather limited data. And then what we did is we basically just uh, randomized the we did an inverse CDF function. We did an inverse cumulative density function. So we had like random value. So we had like random values or a random number generator, and then we put it in the CDF, in the inverse CDF, and then from there we got random values of, so in the inverse CDF, we put in the mean and the standard dev to like simulate the distribution of the data. And then from there, you were able to simulate like 1,000 different synthetic values of friction angle, okay, that falls within the distribution of the data based on the mean and the standard deviation. So that is what we did. That's the bootstrap. That's how we applied bootstrapping in the exercise. So we basically just uh, tried to simulate the range of possible values given the mean and the standard deviation of the data. Okay, so we were able to simulate like 500 to 1,000 values in the exercise. All right, yeah. So that concludes the lecture in Univariate Statistics. I will be also uploading a syllabus, an updated syllabus, and we will probably be having an exam for this, for your univariate stats and bivariate stats. Okay, but it's just gonna be based on the lectures and the Monte Carlo exercise. All right.